So to start on, we're going to start on particulate state of matter. Now, one of your requirements, this is the first chapter in physical science, core. You will be required to know the three states of matter. And as you can see, you've got solid, liquid, and gas. So definitely that's something that you get to know even from Form 1 up until now. So let's have a look at what this entails in more detail. Now, we have the core guidelines. You should be in a very good position to state number 1 under core on the left. You should be in a position to state the distinguishing properties of solids, liquids, and gases. Describe the structure of each state in terms of particle separation, arrangement, and motion, and we'll soon see it. Describe and explain diffusion as the movement of particles, atoms, molecules, or ions. Supplement for now, we will leave it at that. Now, everything is made of particles. The matter is anything, or matter is anything that has mass and takes up space. You should take note of that. Now, on the left, you can see there's a dialog box on the left. So I'll start there. All matter is made of tiny particles, far too small to see, even with a light microscope. The particles are always moving. They have kinetic energy at every temperature above absolute zero. Now, you have to understand that absolute zero is the temperature at which all particles, ions, molecules do not move. Absolute zero is somewhere around minus 273 degrees Celsius. Three states of matter: solid, liquid, and gas. The same particles are arranged differently. So it depends if it's a solid, liquid, or gas. But if it's a solid, the particles will be arranged differently as compared to a liquid or gas. States depends on the particles, how close they are, how they are arranged, and how fast they move. All right. So you can see on the dialog box on the right, if you zoom in on any material, chemists explain that we can see the drop by what we cannot see. All right. So I think we'll get to explain into that. So a drop of water, as you can see, but that's what we can see. And you will find particles in a drop of water. Those particles we cannot see. Now, let's look into distinguishing the three states. Of course, this is where the fun starts. We do have solid. You will find out that states of matter or matter can exist as a solid. It has a fixed shape, fixed volume, cannot be compressed, does not flow, and usually dense. What about a liquid? In the middle, takes the shape of the container, fixed volume, almost incompressible. As you can see back onto the left, a solid cannot be compressed. Solid does not flow, but what about a liquid? Flows and pores, fairly dense. Let's move on to gas on the far right. Fills its container, no fixed volume, so meaning that a gas can spread out, whereas a liquid and a solid, they will not spread out. Gases are easily compressed, and gases flow freely. Very slow density. I think I can use that as a highlight. Okay, now moving on. Now, the same particles are arranged differently. We have probably a much deeper introspection into that. Let's have a look at solids, how they are separated, arranged, and how they move. On the far left, solid. Close together, the particles in a solid are close together. They have a regular pattern and vibrate about fixed points. Liquid, close together, but there is no pattern. Unlike a solid where you can see that there is a regular pattern. But with a liquid, there is no pattern. And in a liquid, the particles slide past each other. They are close together, but they slide past each other. If you go back to the far left, the particles are close together, but vibrate on the spot or vibrate about fixed points. Gas, far apart, indeed, in terms of separation. So if you can see on the top left there, just beneath the heading, the same particles are arranged differently, where it says separation, arrangement, and motion. is how they are being described respectively. So let's go to the gas dialog box. Separation is far apart. Arrangement is random, whereas arrangement for liquid is no pattern, which is almost the same thing as random. Motion, however, liquid, they slide past each other, but if you go to where it says gas, moves fast in all directions. So you can take a moment, you can even pause to take a moment to look at that again. I would encourage you to pause and even take a moment to pause on that. All right. Now let's move on. How particles move. So let's see how particles get to move. Now, let's have a look at motion. Motion links directly to the forces between particles. In a solid, before we get to read about this information, the forces of attraction are very strong. So the particles will vibrate about fixed positions, they cannot move. In a liquid, the forces are not as strong as that in a solid. So particles move around but staying in contact. Whereas in a gas at the very bottom, the forces are very weak and therefore the particles move fast, freely in straight lines. Now let's start from the very top on solid. Vibrate about fixed position. Why? You need to be in a position to give a reason as to why they vibrate about fixed position. Strong forces hold particles in place, so they cannot move around, only jiggle. Liquid forces are weaker, so particles slip past neighbors while staying close. And gas forces are very weak, so particles travel far, only interact when they collide. Now, we have this question to think and to ponder about. So I'll read this question, and of course, you will have the opportunity to stop the recording so that you can think of an answer, probably write it down, and then you compare with the answer on the next slide. I'll read. A substance has a fixed volume but takes the shape of its container. Its particles are close together with no regular pattern and can slide past each other. Which state of matter is this? That's part A. Part B. Give one property of its particles that a gas would not share. Give one property of its particles that a gas would not share. So now you can stop the recording now and write your answer. Press play when you are ready to check. Okay, so now you can, I'm sure you've already pressed play as you are hearing this after pausing. I believe you've already pressed play. Let's go on to the next. If you haven't pressed play, pause. You need to pause right now and read the question again. But I believe if you are hearing this, it means you've pondered the question, you've written your answer. So let's proceed. Okay. Now what we do have here is changing state. Now, what we have is you can add or remove energy and particles rearrange. If you add energy, the particles have more kinetic energy and the object will melt or even evaporate. As you can see from the left, you can see there is melting because you're adding heat energy, and then there is now also boiling after that middle box there, and then there is evaporating. However, if you remove energy from the far right, you have condensation, and from a gas to a liquid, that's condensation or condensing. And then also if you continue removing energy, you end up having it freezing back to a solid. So energy in, that's heating, because the particles are taking in energy. This is going to be very helpful in the not too distant future when we get to discuss about endothermic and exothermic reactions. So here we have energy in, particles gain kinetic energy, move more, overcoming forces holding them together. Melting and boiling need energy in. However, when energy is being taken out, the particles will be losing energy. They will start moving less, and because they have less energy, the forces of attraction become more powerful than the energy they have pulling them together, condensing and freezing them. Now, let's have a look at the next dialogue. Where does the energy go? During change of state, the temperature stays constant. During change of state. So you realize that if you look at this dialogue, this graph, during melting, you can see that it's flat. And also during boiling, you can see that the line is flat. So where is this energy going to? I will be able to explain that shortly after. Now let's have a look at what we have on the far right. The flat parts do matter. Now on the slopes, added energy raises the temperature, moving particles faster. But what happens on the flat paths like melting and boiling? The temperature holds steady even though energy is still going in. Now that energy will actually be breaking the forces between particles instead of speeding them up. So during melting, for instance, you may have your ice block in water, and as you heat that beaker of water, you will find out that the temperature will not elevate or raise. No matter how much heat you apply, the thermometer will continue recording 0 degrees Celsius because the heat energy is being channeled towards breaking the forces of attraction holding some of the ice together. Only when all of the ice has melted will the temperature begin to rise again. You will soon be able to see these demonstrations from textbooks as you study, and as well as some of the links that will be sent to you. Now, I'll have you pause and think. Unfortunately, I think I sent you the template which doesn't have the answers, but anyway, those answers will be provided. Now pause and think. A pure solid is heated steadily until it melts, where while it is melting, the thermometer reading does not change. Explain in terms of particles and energy why the temperature stays constant during melting. So you have to pause now, aim for 2 clear points, press play to mark your answer. So you will have to pause this, and then the answers will be provided for you in the next session or probably tomorrow, because this link or this presentation doesn't have the answers at the moment, but I will do get to provide you the answers. So let's read the question again. A pure solid is heated steadily until it melts. While it is melting, the thermometer reading does not change. Explain in terms of particle and energy why the temperature stays constant during melting. Now, I believe you've already paused, and I will continue, and you've pressed play, but I believe that the answers, if I can then share them with you, is that the energy is being directed towards breaking the forces of attraction. It is only until all of the forces of attraction are broken that the temperature begins to change and increase. Now, let's talk about diffusion. Okay. Now, with diffusion, the spreading of particles from high to low concentration. Definition: diffusion is the net movement of particles from a region where they are more concentrated to a region where they are less concentrated, because the particles are constantly moving. Only happens in liquids and gases, where particles can move freely. So hence diffusion only happens in liquids and gases. Faster in gases than in liquids. Why? Because gas particles are more quicker and are further apart. That's why diffusion is faster in gases than in liquids. Gases are gas particles move quicker and are further apart. So they will often ask you why diffusion happens faster in gases than in liquids. Gas particles move quicker and are further apart. And then also at the bottom left dialog, no steering needed. The random motion of particles does the work. So diffusion, in fact, in gases, there is no steering needed. Yes, it can be accelerated, of course, in liquids, but absolutely no steering is needed even. Now, let's have a look at the right dialog box in the right. A drop of I in water. Now, you can see a drop of dye, a drop of dye in water. So you will see that at the start, dye is concentrated, but over time, the dye spreads evenly without stirring. The color spreads on its own until it is evenly mixed. Now, we have the following. Lighter particles diffuse faster. I'm sharing this, although this is for supplement, because I might want to then assess you both for core and supplement. Now, for also for the sake of knowledge. So let's read the main heading. Lighter particles diffuse faster. We have to understand why this is so. The rate of diffusion depends on molecular mass. The rule, at the same temperature, particles with a smaller molecular mass move faster, so they diffuse more quickly than heavier particles. Why? The particles in a gas share the same average kinetic energy at a given temperature. However, lighter particles reach a higher speed for that energy, so they travel across the space sooner. So we have this gas tube experiment on the dialog box on the right. You can see hydrochloric acid, and then you have what we know as ammonia on the far left, which is orange, NH3. So at the bottom there, you can see NH3 has a molecular mass of 17, which is lighter. So it travels further along the tube before the two gases meet, whereas hydrochloric acid has a molecular mass of 36.5, which is heavier and moves more slowly. And this you will soon see in some of the elaborated experiments. Now, a pause and think moment. Two gases are released at the same time from opposite ends of a tube. Bromine vapor, 160 molecular mass units, and hydrogen, which is only 2. Which gas diffuses faster, and where along the tube would you expect them to meet? So you have to pause and think this through. So I'll allow you to pause, and then I can share the answer with you. Whatever answer you think, you can note it down and reconcile whether it is the same with mine or not. Anyway, I believe you've paused, and we can discuss the answer. Now, obviously, we expect hydrogen to diffuse faster, and probably it will be more than halfway across the tube when they get to meet because it is lighter. Okay, so now we have to just do a recap here. Now, you see, you have to understand that there are 3 states: solid, liquid, gas. The same particles arranged differently and moving differently. For the properties, solid keeps shape and size, liquid keeps size only. Gas keeps neither. Arrangement, regular and close solids, close but random liquid, far apart and random gas. Number 4, change of state. Heating adds energy to break forces. Cooling removes it. Temperature holds during a change. And we need to understand that why the temperature remains the same, because it be used to break the forces of attraction. Diffusion, particles spread from high to low concentration by their own random motion. And then also rate and mass. Lighter particles move faster, so they diffuse more quickly. So you are done with chapter 1.1, and we'll be able to look at some of the assessment questions that will be sent to you tomorrow, and as well as you need to get a printout to fill in those answers and follow the instructions that come through.